Alright guys, here's where we get to the acids and bases parts of equilibrium. This will make up the rest of our unit. I just wanted to remind you of Arrhenius' theory that acids react with water to make hydronium ions, and that bases dissociate in water to react with water to produce hydroxide ions. So this was a very limited theory in that it only considers water as one of the reactants. So we can expand that to include other solvents, which is what we're going to do for the rest of this unit. So the second definition of acids and bases that we will learn is the Bronsted-Lowry theory. So Bronsted-Lowry, two guys, says that acids can donate a proton and bases can accept a proton. So proton, we know, kind of works with H3O plus in water, but in other solvents we just consider the H that's moving around. Okay, so it can only act acidic if a base is present, so there has to be something to donate a proton and accept a proton at the same time. If there were two acids per se, nothing would happen. Alright, I was saying on the previous slide that water can sometimes act like an acid and it can sometimes act like a base depending on what it's reacting with. So we call that amphoteric or amphiprotic. So water or a polyprotic acid or base that has lost one or more of its protons but still has the ability to either gain one back or lose another one can be considered amphoteric. So in the reaction seen here, we have the bicarbonate ion and water reacting, and it can go one of two ways. Water can either act as the base and accept another hydrogen, or water can act like the acid and donate one of its hydrogens to make carbonic acid. Okay, now these do actually have Kc values in real life, and we can see that in the second reaction, it's got a larger Kc value. This means that the products of this reaction are more favorable than the products of this reaction. So what this means is that water and bicarbonate together are more likely to make hydroxide and carbonic acid molecule together. Okay, so in this case, water is more likely to act like the acid and bicarbonate as the base. This isn't a really big piece of it, but it is a bit of an extension, and we'll get into a little bit more of this analysis in a little bit. Alright, so why is this a good thing or a bad thing? Bronsted-Lowry doesn't explain why this transfer of the proton happens. It just explains the process, which we know to be true. Okay, so you can't tell why, just that who's the acid and who's the base. So, and the pro of that, of course, is because you can define an acid and a base in a reaction that doesn't even include water. I know we haven't really seen one yet, but we're going to look at a few of them. All right, so we can explain in more solvents than just water. All right, here's where we need our data booklet. Right in the middle, there is a big long table of acids. So strength of acids and bases is very similar to the way that we worked with that table of reduction potentials. So the strongest acid is actually going to be at the very top on the left-hand side, okay, because there's two columns, and it looks like an acid and then its conjugate base, okay? So the weakest acid will also be on that left-hand side, just at the very bottom. Now, the strongest acid has the weakest conjugate base. So, the weakest base is on the top right-hand side, whereas the strongest base is on the bottom of the right-hand side. All right, so simple. Just take a quick look at that. Label it as SOA and, SOA. Strongest acid, so SA and SB at the bottom, kind of like we did on that previous table. Alright, and just like reaction spontaneity earlier on in electrochem, we can also say whether a reaction is favorable for an acid-base reaction, just looking at that table again. So the strongest acid above the strongest base, you're going to know that the reaction proceeds more to the products, that they're going to produce more products, and that they are favored. And vice versa, what looks to be non-spontaneous over here would actually be reactants are favored. So again, non-spontaneous meaning it's going to keep most of its reactants anyways. All right, so we can go through some of these examples here and talk about which side is favored. All right, so we see in our first reaction here, I've labeled acetic acid as the acid, as it has obviously lost an H, and water as a base because it has gained an H. If we look at our acids and bases table, we find that acetic acid, or vinegar, is much lower on our table than water as a base. So we have to look for water in the left-hand column of the compounds and acetic acid water in the right-hand table column of compounds because it's base, and acetic acid in the left. Acetic acid is lower than the base, so we find that this reaction is unfavorable. So reactants are favored. Sorry guys, this should be an acid and this should be a base. In our next reaction, we see that ammonia is gaining the proton, so it is the base, and phosphoric acid, clearly the acid. Phosphoric acid can be found higher, again, than ammonia. So phosphoric acid is about 3 down from the first gray bar, and ammonia is close to the bottom. So this is a favorable reaction, and the products, my goodness, are favored. HCl is the acid in this case, water is the base. We find that HCl is a very strong acid, so this is, again, a favorable reaction, and products are favored. In fact, this goes almost 100% to the products. Water plus water. One water molecule is acting as the acid, one as the base. Water as an acid is at the very, very bottom. Water as a base is at the very top. So this favors reactants. Water doesn't really react together and ionize in this way. Alright guys, here's a little chart of how to predict acid-base equilibriums. So list everything that is possibly present in an ionic form and include water if it's aqueous. Label all possible acids and bases. Identify the strongest acid and the strongest base using the data table. And then write the equation with the strongest acid, strongest base, and predict which side equilibrium is favored. Alright, so predict the Bronsted-Lowry reaction between aqueous sodium hydroxide and vinegar. So let's go ahead and start with labeling everything that is present. So aqueous, right away, I have water. Sodium hydroxide dissociates in water. We have Na+, OH-, and vinegar is acetic acid, so CH3COOH. Water can act as an acid and a base. It's amphiprotic. Sodium is nothing. OH is obviously quite basic. And acetic acid is acidic. Looking in our data tables, water is the weakest acid and the weakest base possible. So we find that obviously hydroxide is the strongest base. Acetic acid is the strongest acid. When we write our reaction, we find that acetic acid gives up a proton and it is donated to hydroxide. So this was our acid, base, conjugate base, and conjugate acid. Alright, looking in our table of values, strongest base is much lower than the acid here, so products are favored. That's it. Very simple. Alright, one more here. So, predict the Bronsted-Lowry reaction between aqueous ammonia and nitric acid. So, aqueous ammonia is water, ammonia, NH3. Now, nitric acid is one of the strong acids. It's listed in the top 6 of our chart there. Anything that's in that very top section, as soon as it's put into water, it ionizes immediately into H3O+, and its conjugate base. So we always consider a strong acid as just simply H3O+ and its conjugate base, so NO3-. Okay, so this is the case with all other strong acids. So perchloric, hydroiodic, hydrobromic, hydrochloric, sulfuric, and as we have here, nitric acid. So water, again, acid or a base. Ammonia is the base. Hydronium is clearly the acid. And NO3 could act as a base, but anytime this is considered, so our strong acid, its conjugate base here, we're always going to hit water first. Okay, so none of these will ever really be considered in the running for strong base. So ammonia is our strongest base here and our strongest acid. So we get that NH3 and H3O+ in equilibrium make NH4+ and water. Okay, so this was our base, acid. This came from our conjugate base, or sorry, from our base, so it must be the conjugate acid, and water is the conjugate base. Alright guys, here's the homework. So there's lots to do. However, I put this video up early so we can have time to work on Friday as well. And you guys can have 2 kind of work periods. Again, a reminder, we have our quiz tomorrow as well. Your Le Chatelier lab will be due on Friday. So lots of things to work on today.